going to see how we can implement a low pass filter and a high pass filter and use them to remove motion artifacts and any high frequency noise that are present. So how we perform this is using an HPF that is placed at really close up to 0.5 Hz. We remove off the baseline wandering or the power line signal that has been included into the signal. While using LPF, we can remove the high frequency noise. In my experiment, I have used one HPF at the cutoff 0.5 Hz, while 3 different LPFs at different cutoffs to see where maximum signal is produced and maximum noise is reduced. In LPF design and HPF design, we first designed the transfer function for it, and then try to evaluate back our coefficients so that you can reduce it into a difference equation and use it to design our LPF or HPF required. Now to perform this, let's see. So here I have written design for first order LPF, which is given by the formula h of z as k into z plus 1 divided by z minus a, where z minus a will represent the pole of the filter, while z plus 1 will give you 0 at the max frequency, which is pi or 0.5. Now design k, the k is basically normalizing factor, while a which is calculated as this in this way, and calculation of pole is based on your cutoff at a frequency given by these conditions. In the HPF design is a similar case. We can also obtain this filter design by substituting z as z into e power j pi. So this would be the design. That changes at plus 1 becomes minus 1 over here, and rest others are given over here. So substituting fs as 100 Hz, which is our sampling rate for the data given here, and fc as 0.5 Hz for HPF, and for LPF substituting these 3 different values as mentioned here, we get different h of z designs, and then exploring them backwards or reverse engineering them, we can get our filter coefficients. Okay, so this is the HPF design. You see the difference equation is given over here, right? And then similarly we have LPF for 30 Hz, which is designed in this way, LPF for 10 Hz, and so we have LPF for 5 Hz. These are all simple difference equations which we can directly implement them. All we would need is certain storage elements like output previous, which would store your previous output value, and input previous to store your previous input values, so that we can design the filter easily. Okay, now I have used them as functions. Let's see outputs of each of them. So in my case we have LPF 30 Hz output as output 2. So let me place it here. So let me explain you. The blue colored data is the blue colored signal is the original PPG signal, which you can see is quite corrupted with noise, while the red colored ones is the one that which is after removing the baseline filter. In my case, the baseline wander is very slow, or it's really not directly visible, so not much of effect is seen. While the above one is the output of your LPF, which slightly is smoothened version of your input. Basically it has removed the high frequency noise. We still need to remove further noise so that we can obtain a smoother waveform. So we can think for output 3, which is the output of LPF with 10 Hz cutoff. see the data has become slightly more smoother. We still need to smoothen out more noise, as basically the heartbeat and the signal that comes out for it in the BPG signal generally is of the range 0.5 to 5 hertz. This is the maximum, this is the entire range for our heartbeat signal. So the rest other can be considered as noise. So let me show you the output of the next filter, which is at 5 hertz. As you can see, it's further smoothened, and you can see the peaks have got slightly amplified. So this is the effect of low pass filter. It relatively suppresses your high frequency component so that we are able to observe cleaner waveforms. Still more smoothing can be done, but it will be at the cost of loss of PPG data. As you can already see, the diastolic peaks, which are the minor peaks in the data, have really got suppressed to a large value, suppressed by a large value.